So the name of this section is called Definite Integrals, and we're really getting close to the fundamental theorem of calculus, which is going to help us with this situation that we're looking at, which is coming up with the area under a curve. So what I'm going to do is I'm going to start out with just the idea of net area, and then I'm going to expand on that and get a little more precise with it. And then I'm going to do an example problem that I think will take care of most of what you guys are going to look at for this. And then I'll end up doing two more example problems, but the first example problem is going to be really like tying everything together. So we have this idea of area under a curve. And so far, and we're still talking about Riemann sums right now. Okay, so far all we've talked about is when our curve is above the x-axis. And we've been getting these areas by slicing these into rectangular areas and then adding up all those areas of the rectangle. So again, everything that we've looked at so far is when the curve is above the x-axis. Now, of course, all functions are not above the x-axis. And so then how do we deal with that? So, let's think about how we are dealing with Riemann sums. Okay, so what we're doing is finding a small little interval, like a subinterval, and we're going to use that as our base, and it's going to be the same subinterval as we go all the way down. And so I guess for right now, let's just look at this part from 0 to 10. So we'd find the same base, however many subintervals we wanted to break that down into, that would be our n. And then what we do is for each subinterval, we choose a height by picking some x value on that subinterval, plugging it into the function, and getting a height for each of those little rectangles that we've created. We multiply those together to get the area of each of those rectangles, and then we add it all up. And hopefully you understand that the more subintervals we had, or maybe better at this point to say, the smaller the change in x, that delta x is, the more accurate our area got. And when we were plugging in that, right, we were calling the x sub k star, right? That was just like any point on our subinterval that we were using to get the height of the rectangle. And that would usually refer to the left or right or midpoint of those rectangles. When we plugged that in, we were getting positive heights. And so then we were doing a positive base times a positive height. And then we would get the area. Now, of course, when we move to the interval from 10 to 20 here, we would still treat it the same way. And so we would have however many subintervals going along here that we were looking for. We would use that delta x as our base for our rectangle. And then somewhere in each of those little delta x's, we would pick a value, this again, plug it into our function and get a height. Now, we would still take that height and multiply it by the base for each of those rectangles and each of those subintervals, and we would get this area. However, when we use any value in this graph from 10 to 20, and plugging it into f, we were getting negative values. And so that's kind of the idea of this net area. Anything above the anything above the x-axis would yield a positive area, so these two would be positive areas, and anything below would be a negative area. So, for instance, the net area on this picture, if we were doing it on the interval from 0 to 30, our net area would be 100 minus 50 plus 30, because we're going to count anything above the x-axis as a positive area and anything below as a negative area. And so then that would be a net area of 80. Okay, and then to just expand on that, just to kind of drive the point home here. If we play around with our intervals, we would get something completely different. So let's say we do an interval from 10 to 30. Now we would have a negative 50 area plus this 30, and so then our net area would actually be negative 20. So the only thing, like I kind of remember this from last year when we talk about the AP, be careful on the wording of the question, because if they're talking about net area, it's very straightforward. Positive, negative, positive. But if they're just asking for some kind of absolute value area, just understand that this is an area of 50 that's below the x-axis, and so we refer to it as a negative 50 when we're talking about net area. So that's the whole idea of net area, and now I'm going to get a little bit more precise on it with some of this notation. And again, if you feel pretty good with Riemann sums, then this isn't really anything more. Again, all we're doing is finding little areas of little rectangles and adding them all up. It's more of the notation that can throw you off. So let me go and do that. So I'm going to run through just some of the pictures that they're using in the book. And I'm going to hit some definitions on the way. And hopefully this will make this stuff fairly straightforward. You know, they have this, and this is at the top of page 366. It says the Riemann sum here, and again, let's look through what we're saying with this here in a second. Approximates the negative of the area of the region bounded between x-axis and the curve. Well, that's only because we're down here below the x-axis, okay? It's not always negative, right? It could be positive, it could be negative, just depends on where that curve is with the relationship to the x-axis. And so, you know, again, it's the notation that really throws us off here, I think. And so what we're saying is we're going to get a negative area because this curve that we're looking at is below the x-axis. But what we're doing is we're just breaking this from this interval A to B into however many rectangles we want. Okay, and we're going to look at that again down here. But as of now, right, you know, this is the first interval all the way to however many intervals we want. And again, you can think about this n value as the number of rectangles that we're adding up. And again, the summation sign means add up what? What are we adding up? Well, we're adding up the area of a rectangle every time. Remember how this is. We would find this change of x, and again, the way you find change of x is do b minus a and divide it by however many intervals you want. And that gives you an equal amount of a distance. Let me see if I can say that better. The base of our rectangles are not going to change, and they're always going to be this change of x. Okay, and so if we did 10 intervals, right, we do b minus a divided by 10, and that would give us our base that we're going to keep using, and that's why it's going to be summed up. Every time we do a new rectangle, again, this is the area of a rectangle, we're going to multiply it by the base times the height. Okay, and we're going to get that height by plugging in some value x that is on each of these little subintervals, each of these little rectangles. Plug it in and get the height. Okay, so that's what this is saying. So now let's look at that a little bit closer. And this is just on the next page on 367. Right, so we're going to find the approximate net area. And I want to pay attention to like what they're saying here is, you know, when we are saying, okay, let's get a good idea of what our net area is, then you can just break it down into, you know, however many intervals you think is appropriate. But what we're doing is, okay, so in this case, we did 6 subintervals. We have 6 rectangles. 1, 2, 3, 4, 5, 6. Okay, and then each of these is going to be equal, and that's going to be our change in x. And so then it's going to be, this rectangle would be this base, this change of x, times some point on here plugged into our function to get the height. And so then our approximation is going to be positive here, but then it's going to turn to 3 negatives in a row and then 2 more positives. We're add up all those areas, positives and negatives, to get the net area, an approximation of the net area. Now, of course, if we say, well, I want a better approximation, but we're still approximating, then I'm going to bump up the subintervals. I want more rectangles to cut up and add. Okay, and then there's going to be a kind of like a definition that we have to understand here. Basically, the book is going to call this the slice and sum method. Okay, So what we're doing is slicing our areas into smaller and smaller rectangles and add them up, slice and sum. So you're probably going to see that at some point, and that's what they're talking about. Okay, but when we have 40 subintervals or 40 rectangles, we get a better approximation, but yet it's still an approximation, but it's still the same thing. Our change in x is going to be smaller than it was over here because we have more, and this is how it's going to get us more accurate because we're adding more and more and more. Okay, you can see, like, look how big that area is above the curve. We don't even want that. And these areas that are below the curve, we don't want these. Okay, and you can see how much smaller those areas become by just going all the way to 40. But it's the same thing. We're just going to find the area of 40 rectangles and add them all up. Positives, negatives, positives. Okay, again, we're still at an approximation of the net area. But we've sliced it into 75 subintervals or 75 little rectangles. But we're doing the same thing, right? We're finding the area on each of these 75 little rectangles, or thin rectangles, I guess. But we're getting a better approximation of the net area because we keep slicing it smaller and smaller and smaller. And we're going to take all 75 of these and add up 75 different areas. But then we come over here and now we're equal. This is what the net area actually equals. And, again, what this is saying is if we come up with an infinite amount of rectangles, right? And that's forcing, when we say an infinite amount of rectangles, then we're forcing this change in x to basically go to 0. And of course, we can't multiply by a 0 and add all that up. We'd have 0. So as it approaches infinity, as we approach as many rectangles as we can possibly come up with, then we actually get an actual value of the net area. Approximations, exact value. Okay, and so here's our definition of a net area. The idea is just what I said in that last one, right? All the areas that are below the curve and above the x-axis contribute positive areas. Anything below the below the x-axis and above the curve contributes negative areas. Okay, but, right? As we go to an infinite amount of rectangles, we're still going to just find the area of all of those infinite rectangles and add them up to get the exact net area. So I'm not going to spend a lot of time on this definition, but we do need to understand that, and this was a question that was asked when we first started talking about Riemann sums. We don't have to have the same size intervals to do a Riemann sum. Okay, so when we talk about, what we were talking about before is a regular Riemann sum. And a regular Riemann sum is where all of our intervals are the same. That's that change in x. Okay, but what we're saying here is a general Riemann sum is exactly the same. Okay, it's the same idea, but the difference is that we're going to have different size intervals as we go. And so then, then we're going to actually label, in this case, the change in x. So our base of all our rectangles would have an individual assignment as opposed to the way we were doing it before, where it was just a change in x is all the same. But all this thing is saying is that, it's saying exactly the same thing, only that we don't have to have our delta x, our change in x, being equal. We can have them at different sizes. Okay, so that's all. When you hear something referred to as a general Riemann sum, just understand that the base of the rectangles change, or the delta x changes on each of the intervals. But other than that, it's basically the same idea. So I think this is a good time to take a look at an example problem here. And this is number 16 out of the book. And this is exactly the same as the first section. There's two sections here where they're talking about Riemann sums still. So this is a good review for the Riemann sum from the last section. You're going to be asked to do two different things by finding the area. Okay, so we're still finding area under a curve throughout most of this section, or maybe all of this section, really. But you're going to be asked to do it with Riemann sums and with geometry. Okay, so pay attention to what they're asking you to think about. And so this section says, the following functions are positive and negative on the given interval. And I think, like I said, I think this will take care of everything for us here. It says sketch the function on the given interval. Okay, so here's from 0 to 4. I kind of made it a little bit bigger, and I'm going to draw the rectangles on here. So there's part A. Part B says approximate the net area bounded by the graph of f and the x-axis on the interval using a left, right, and midpoint Riemann sum with n equals 4. So I think what I'll do is just do one of them. I think that, I don't know, maybe I'll change my mind, but I'll at least do the left and then see how I feel, if it makes sense. So we're using Riemann sums to still approximate the net area. So, and they want it in 4 subintervals. So let's talk about how we get our subintervals. So that's going to refer to the change of x. And, they gave us that they want 4 subintervals here. So we're going to take b minus a and divide that by the subintervals. And so then we're going to get a change of x of 1. Okay, and I am going to do a left Riemann sum first. So for the rest of this problem, this is going to be true. You don't have to redo that. Okay, so let's take a look at left first, left Riemann sum. Okay, so then that means that the left-hand side of the rectangle is where we're going to get our height. So for this first one, right, we're going to use this. Okay, our second one, there. Our third one, here, and you see we get a little negative there. And then our fourth one is going to be kind of weird. Since we're using a left Riemann sum, we're only getting there. Okay, so it probably going to be, I said maybe I wouldn't do more than one, but I'll do at least 2 so you can see what we're looking at. And so then how does that work? Well, we need to find our change in x. No, I'm sorry, we found our change in x. We have to find our, we still need to find our x sub k star, which is, again, any point on these intervals, but since we're using the left-hand one, we're going to use the formula from the book in the previous section as a plus whichever interval we're on minus 1 change in x. And again, the way this works is, okay, we're starting at our first, at our original left-hand side of our interval, here at 0 in this case, and depending on which interval we're on, we're going to find the point that we want to plug in by going from a, adding how many changes in x we need. So again, if we want to do the second, if we're on the second interval, that would be a plus 2 minus 1 would be 1 change in x. So here is the height we would use on our second interval. Okay, the third interval, which would be here, we're going to use a plus 3 minus 1, so 2 changes in x's. So a plus 1 change of x, 2 changes of x, that's what we're going to plug into our function to get the height. So in this case, right, for what we have, we're going to say that this is going to be 0 plus k minus 1 times 1. So all we're doing is plugging k minus 1 into our function. And then again, the k is going to get taken care of with the notation here. Okay, so we're going to do 4 rectangles. Right, that's what that's referring to. 4 rectangles. And we're going to find that by plugging in that as our height and this as our base. And we're going to multiply them all up. Now I'm going to use the notation to figure this stuff out, even though 4 is a pretty easy one. I'm not really sure if they, how they want you to do it, but I suggest, this way, a good practice on all those summation formulas. Okay, so again, the reason that k is okay here is on our first interval, right? We're plugging in 0, so f of 0 gives us some value, and then if you think about our intervals, right? It was really 0 to 1, 1 to 2, 2 to 3, 3 to 4. Okay, and so that's how we're going to get our height on all these. So let's simplify this down a little bit. So actually we have f is really 8 minus 2 times k minus 1 squared. That's going to find our height of each rectangle, and then we're going to multiply it by our base of each rectangle. Now we got to do a little simplification here. And then I'll just move the 1 out front here. I mean, it's irrelevant, right? But just keep in mind that we do have a base that we would need to multiply this all by. Oh, I lost my base. So it's still there. We don't need it in this problem. All right, but then we have okay. So now we're going to use this idea of those summation formulas. All right, so I'm going to break all these down, and I'm going to lose the 1 while I do that. So really we're finding the summation of each of these individually. And I'm going to take the 2 out front here. These are all the rules that we talked about before. And I'm going to take the 4 out front here. All right, so then what these summation formulas tell us is that the first one is going to be 36 because we take the 9 times the 4. Then we're going to subtract 2 times, right now this is that squared one. So then it's 4 times 5 times 9 all over 6. And then we're going to add this to it. Again, these are on page 357. And then I'm going to add those up. Hold on. Okay, and you work all that out, and you get that the net area is 16. So let's take a look at the right hand, or the right Riemann sum now. And I think it's worth doing so that you can really see the, how different these approximations will be, or not different. I don't know. I haven't done it yet. But when we're using the right endpoint of our rectangles, everything's the same, right? We still got our change of x being 1. This is still the same problem. But now look at the way our rectangles match up compared to what they did before, right? This one isn't quite as big, but look at the difference. And this is like a really crazy one, right? Like we have to use the height no matter what it is at that right hand endpoint, And so we're actually getting a negative value of our area. For all of this, that's actually positive. But this is what happens when you have such huge subintervals, is that you're really getting an inaccurate estimate sometimes, depending on the way the shape of everything goes. Okay, but everything else is the same, right? We're just finding our value that we're going to plug in for our height, looking at the right-hand side. So, right, for first interval, second interval, third interval, fourth interval, right? How do we get there? By the summation stuff? Well, we start at A, and we add, for the first interval, we add one change in x, one base, and use that as our height. Then for our second interval, we plug in 2 and use that as our height. And then we plug in 3 and use that as our height, and then plug in 4 and use that as our height. Okay, that's the difference between the left and the right hand, just as a little reminder. So, okay, so let's go through that again. So we're still looking at 4 rectangles. I guess we should do this, right? So then this, for our case, would be 0 plus k times 1. So actually just k is what we're plugging in now. So then it's going to be f of k times that change of x, which is 1. So then it's going to be 8 minus 2k squared, and of course times 1. And I'm going to drop that now. And I'm still going to use the summation formulas to do this. So really what we're doing is 4 rectangles. Right, I'm breaking this up. So then it's going to be 32 for the 4 times 8 minus 2 times, now we're using the k squared one, so 4 times 5 times 9 over 6. 21, 180 over 3. Right, I did that right, 20 times 9, 180 over 3. So then, so we're getting a negative 28 when we do it that way. And comparing the two things, we had a 16 on the first one, but we almost had no, because we were using a left hand. Since we were using the left-hand Riemann sum, we almost had no negatives. And now we have, since we're using a right-hand one, we have all this negative area that we're adding up. And, some of it is unnecessary. Like, look at all of this stuff and all of this, right? We're taking away some of the positives. So, again, these are just estimates this way. And then to answer the last question, right, we're getting all from 0 to... well, whatever this value is contributing positive areas, and from that same value over to 4 is contributing negative areas. They want you to do that on the graph. So hopefully that makes you feel pretty good about kind of the idea, and let's look at the next idea. So again, these are just the pictures out of the book, and this is a very precise definition of definite integral. But I think it's easier to wrap your head around what's going on down here. But I just want to point out a couple things up on this first one, and you should totally read it. But they're saying as the change of x approaches 0. Okay, so as this gets closer and closer to 0, and of course we can't do that without the idea of a limit, because then we'd be adding a bunch of 0 areas, because we'd be multiplying our base as 0. But we're going to change up the notation of how we write this. And this is going to take care of having to take a limit at all times. But some things I think are important are that this works for any value that you pick that is on those little rectangles. The height that you're going to get is going to work for any of these. You can do the left or the right or the midpoint or anything in between any of those. Okay, so let's I suggest you read that, but let's take a look at what's going on down here. And so what we're saying is that that this, right, I think we agree from the last couple slides that this, if we slim up those subintervals or those little rectangles so that we have an infinite amount of them, then basically what we're doing is saying the change of x is not even there. We add up all those, that slice and sum idea, slice and sum method, then we would get an exact value for an integral. And they're saying, well, okay, so we're going to change it up just a little bit on us. And again, we're inching towards something called the fundamental theorem of calculus. Then these two things are going to be the same. We're just changing notation on us. Okay, so we're finding areas, and think about what this is. And there's a little pullout down below this picture in the book on page 368, and they talk about Leibniz's ideas. And so I'm kind of using what they say there. This d of x, before we said that that's just going to be the variable of integration, and that's still true, but Leibniz thought of it as the change in x. So this is just the base of each of our little infinite amount of rectangles. This is going to be the base. And this is going to be the height for our infinite amount of rectangles. Okay, now over here what we were using, they call it the upper limit of summation, the lower limit of summation. But now they're saying lower limit of integration and upper limit of integration. So when we talk about our interval, like on that previous example, 0 to 4, we're going to write a as 0 and b as 4. Now these don't match up in quite the same way, but when we went through that weird process of figuring out which values we're going to plug into our function, that kind of starts us at a and inches us down by a little bit of that change of x, depending on which subinterval we wanted. Okay, and so that's getting taken care of by writing it this way. And so this is like an elongated S, and so we're summing, just like this, we're summing up all of these areas from this to this. This is our interval, like our boundaries. So from this value to this value, we're going to sum up all of our rectangles. Okay, so time for another example, and this is just the section 21 to 24. We're just matching up what I just talked about on that last slide. Like, let's write it in the new notation. Okay, so here's how it works, right? Here's our interval that we're looking at, and that's going to be our lower. What do they call that? They call that the lower. Oops, where'd it go? The lower limit of integration is -2. The upper limit of integration is 2. So then we're going to write that, right, with our big integral sign from -2 to 2. So we're going to sum up all of our rectangles that we find between those two endpoints. And our f of x, right, and think about like how we did this before. This is like plugging in each of these values into f of x. So what is our actual function? Well, our actual function is going to be 4 minus x squared dx. All right, so here's how, kind of going in the opposite direction. How are we going to use this to find area under the curve? Okay, so now in this next section, the 25 to 32, right, they're asking us to use geometry, and then in parentheses, not Riemann sum. Okay, so just pay attention to what they're asking you to think about here. Okay, so and do the way they want you to do it, because you'll be asked these kinds of questions. So sometimes they're going to ask you to use Riemann sum, sometimes they're just going to say geometry. But we're going to break this down into our different intervals, okay? And so here's the way we look at this. Okay, this is saying add up all the rectangles, an infinite amount of rectangles, in between -4 and 2. So that's the first thing that we're going to start with. Our interval that we're looking at is -4 to 2. Okay, so we're going to get negative areas and then positive areas. All right, so that's the first thing. We're going to find we're going to find the area of all of this, and then we're going to find the area of this other triangle. We'll do that in blue for you guys. We'll do that in green. We haven't been doing any green. Okay, and I picked a pretty easy one because I just got to do triangles now. But you may have to do circles, you may have to do trapezoids, and they do give you the formula for you guys that don't remember the formula of a trapezoid. They give that to you on page 370. I actually don't need it on this one, but you usually do need a trapezoid one. Okay, so again, they're asking us to do something very specific here. They just want us to find the area using geometry, sketch a graph of the integrand, which I already showed you that, and show the region in question and interpret your results. Okay, so what we're going to do is, starting from left to right, we're going to find our negative area first, right? And so, we're talking about this formula. So it's going to be a -1/2 base. We'll count the base as 1, 2. So 1/2 times the base times the height. And I guess this is where the negative would come in. I guess we should use a negative there as opposed to out front, but I think you guys can figure that. I think you guys understand that, hopefully, right? And so then what is our value here? Okay, well, so this is at -4, so we can find that value by plugging it in here, right? That would be a -8 plus 4, so it's a -4. I already wrote the I already wrote it out, the negative, so I'll use a positive there. All right, and then we're going to add. Oh, you like how I did that in the wrong colors? No. All right, so we're going to add. Oh, did I switch back to green there? Right, in your minds, just look at that green as red. Well, I guess if you're colorblind, I guess you don't even care. Sorry if you're colorblind, sorry. So then we're going to add a 1/2. A base in this case, we're going from -2, so 1, 2, 3, 4, a base of 4. And then we're going to multiply it by the height, right? And so we can find the height the same way. So we have we're down here at 2. So we can plug in 2 here. So 2 times 2 is 4, plus 4 is 8. All right, so then we have a -4 from the first triangle, plus 16. So the net area from -4 to 2 is 12.